Okay, so the van der Waals equation doesn't make a lot of sense to use if you are at room temperature and pressure. We've already discussed that that's where the ideal gas law works really well. But let's do that. Let's do a comparison between the van der Waals equation and the ideal gas equation. So let's do what's the ideal gas law pressure if we have, that's supposed to be ideal, 1 mole of nitrogen. We keep using nitrogen because it's a convenient gas to use. It's one we're all familiar with. Nitrogen gas at 300 Kelvin. All right, so that's, and we need a volume in 25 liters. So that's going to give us close to atmospheric pressure. So we can plug into P equals nRT over V, right? Just use the ideal gas law, equals about 1 bar if we put in all of the constants there. I'm skipping past the calculation here. You can double check my work. It's 0.99774 bar. Now, if we want the van der Waals, PVDW, our equation then is, as we rearranged earlier, RT over V bar minus B minus A over V bar squared. All right, so we need to look up A and B. You can find these in a table in your textbook, 1.3661. This version uses bar instead of atmosphere, unlike the table I showed in the last video. But you can easily convert between the different units. And then B of 0.038577 liters per mole. If we plug those in, we get a value of 0.99710 bar. So we can see there's very little difference, only a 0.3% difference. So there's really not a whole lot of point to going to the trouble of using the van der Waals equation if we're talking about sort of places where ideal gas law works well. But let's change this to, what if we have it compressed to a much smaller volume? What if we decrease the volume from 25 liters to just 250 milliliters, 0.25 liters? So 100 times smaller volume. So the pressure should go up about 100 times. So the ideal gas law, it does exactly that. You just multiply it by 100 and you'll get the same answer, 99.774 bar. Because according to the ideal gas law, they're just directly proportional to each other. If we do the same thing with the van der Waals equation, though, we get a slightly different answer. We get 96.122 bar. And now we see there's a 3 bar difference. Or if we want to do it in percentages, it's about 4% difference. So we can see now that we're getting to higher pressures, the ideal gas law is not performing as well, and the van der Waals makes a much bigger difference. One thing I'll just say here to finish up our discussion of the van der Waals equation. Oh no, I wasn't. I am recording. Okay, sorry, I thought I wasn't recording. To finish up our discussion of the van der Waals equation, is the van der Waals equation has a nice conceptual framework, and we have this A constant and B constant that we can understand sort of why they're there and what they represent about the molecule. But it doesn't work that well as you get to more extreme pressures, especially. So one equation that you can use to sort of correct for this is what's known as the Redlich-Kwong equation. This is one that's so these are two scientists that came up with this, Redlich and Kwong. They, if I remember right, they worked for ExxonMobil, something like that, when they came up with this equation. And so this has its own set of corrections. So P equals RT over V bar minus capital B. And now we have a more complicated expression here for this other term. The first term is very similar to the van der Waals equation. The second term is not. There we go. So this is the Redlich-Kwong equation. And this is a more accurate equation than the van der Waals equation as you get to higher pressures. This is empirical, based mostly on experimental observations. And we can see a comparison between the ideal gas law and this Redlich-Kwong equation here in this figure from your textbook. So this is ethane at 400 Kelvin. The solid line is the experimental data. So this line right here. And van der Waals equation is the dot dashed line, so this one here. So it works pretty well up to at fairly low densities. So this is moles per liter in density units here. and we can see the pressure on this axis here. But as we keep increasing the density, as the pressure keeps increasing, we get pretty large deviations as we get to really high densities. Redlich-Kwong equation is the long dash, and so we can see it works much better, even up to fairly, much higher densities. Peng-Robinson is a different equation of state, like the Redlich-Kwong equation that you can use, and it works better than van der Waals, but not as good as Redlich-Kwong. And so that's just an example of, we're not going to spend a lot of time with the Redlich-Kwong equation, but it is an example of how we could, go further with this. If you're actually, doing calculations involving gases that are under non-ideal conditions, you're probably not going to use the van der Waals equation. You're probably going to use something like the Redlich-Kwong equation instead. But the van der Waals is nice for understanding conceptually why we need to make corrections and how we might go about doing those corrections.